Hi, welcome to this video about LIPSK by Xaoc Devices. LIPSK is all about inverting bits, either manually or with CV. Nothing more, nothing less. LIPSK is part of the LEIBNIZ binary subsystem, an interesting range of modules that makes it possible to deconstruct audio and CV into gates, and simply because of the binary nature of these gates, the system gives us access to unique manipulation options. Reconstructing this binary information into an analog signal is handled by DREZNO, which is the core module of this system, and yields anything from pseudo-chaotic LFOs to wave-folded sounds, gate patterns, bit crush, sample rate reduction, CV turns into gates, gates turn into CV, etc. In this video my main focus will be on LIPSK, but it's impossible to use LIPSK standalone, so I'll be linking it to DREZNO and show you how inverting bits can be a really powerful tool that adds a lot more features to the system than you might first think. Along the way I'll demonstrate some features of DREZNO that I didn't get around to showing in the first video simply because that one was already way too long. Thanks by the way to Xaoc Devices for making this video possible, and a heartfelt thank you to everyone for the support on this series. Let's listen to some patches first, and then I will show you a diagram explaining the function of LIPSK, and after that I'll just start patching cables to show you firsthand what LIPSK can do. Let me try to explain what LIPSK does by showing you an example using a saw wave. First, I'll take another look at how the ADC side of DREZNO extracts bits from an analog signal. For this example, I'll be only using the 4 most significant bits, which in the diagram will be bit 5, 6, 7 and 8. Let's start with bit 8. As you can see, there's a saw wave, which we can split into 2 halves. When the signal coming into the analog to digital converter of DREZNO is below the line, bit 8 will be 0, and when the signal is above the line, bit 8 is 1. So whatever that wave or signal is, when it's below 0 volts, bit 8 is 0, and when it's above 0 volts, bit 8 is 1. To understand how bit 7 works, let's divide this in 2. Now you need to look at the top and the bottom half separately. Whenever the signal is below the dotted line, bit 7 will read 0. This is true for the bottom half as well as the top half of the diagram. So when the signal is here, bit 7 will be 0 as well. Whenever the signal crosses the dotted line, bit 7 will be 1. So here, bit 7 is 1, and here, bit 7 is 1 as well. If we would write down this signal using only 2 bits, which would be a really rudimentary representation of the saw wave we started with, we would see these binary numbers. Now we can of course keep dividing these ranges into smaller portions, and each consecutive half is represented by a less significant bit. If we do this for 4 bits, this is the result. Now if we start inverting bits with LIPSK, and let's just for the sake of this example invert bit 7 first. Wherever there's a 0 extracted from the analog signal, it gets inverted into a 1. And instead of these numbers, we get different numbers. What this means is that the wave at the output of the DAC converter of DREZNO will be changed, because the voltages that are associated with the new numbers are not the same voltages that were sent into the system in the first place. Instead of the saw wave, which is present at the input, part of the wave, the part that's encrypted by bit 7, gets shifted around. Perhaps it's easier to see if you just look what happens when the most significant bit gets inverted. And to the right we can see what happens to a saw wave when we invert both bit 7 and bit 8. And you might rightfully think that this is a really boring patch, but look what happens when I start inverting bits. So let me invert the 8th bit, being actually bit 7. Let me invert the 7th bit. Let's invert both of them. And I'll just experiment inverting different bits to see and listen what it actually does with the wave. I'm still just using the output of the DAC output, which is going through the scope, to control the frequency of a synthesystem VCF, which I'm using to filter some noise coming from orbit 3. You'll notice that when I invert the least significant bits, you can't hear much of a change. And as you probably remember from my last video and the prequel video, this is just because these control really small changes. You could compare changing one of the least significant bits to changing 1 pixel in every 200 pixels in a picture. You won't notice this unless you start zooming in really closely. Now, instead of me just pressing buttons here, let's use the CV inputs or gate inputs of LIPSK to automate this. And I'll just use a triangle LFO that's half the frequency of the saw wave we're sending in to modulate LIPSK. So even though these are gate inputs, you can also send in CV. Of course, these inputs will only react if the CV exceeds a certain range. Let me send in another LFO that's related to the saw wave. This one should be the same speed as the saw wave I'm sending in. Let's send this to the most significant bit. And whenever you manually invert a bit and you send in CV or gates to modulate this inversion, the inversions actually just stack up. So you can see that bit 6 is being inverted. But when I manually invert it, and it receives a positive gate signal, it actually inverts it again. And we all know that when we invert something 2 times, we just end up what we started off with. Now, if I, for a moment, use an oscillator to actually send into the filter. can hear how you can create really interesting modulation with DREZNO and LIPSK. Without even starting to manually change up bits by using the front panel jacks of DREZNO, which you can of course also do. Please keep in mind that whenever you patch a signal into the bit inputs of the DAC stage of DREZNO, this will always override everything else that's happening. So let's try making this a little more interesting by using one of the bit outputs of DREZNO to patch into the gate inputs of LIPSK. So now I'm using the binary information that's extracted from the analog signal by the input stage of DREZNO to invert the bits before they're going back into the DAC output on the output stage of DREZNO. Now I've been ignoring these sliders for the most part of these videos, but what you can do with these, when you watch the bottom trace on the scope, which is the output, you'll see that when I increase this slider, you actually offset the signal. Which could be something you really need in your patch. For example, when you're using this to open and close a VCA. And this slider to the right here gain stages the output. So sliding this up actually increases the amplitude of the output of DREZNO. Let me patch up a quick envelope here using another output of DREZNO. And if you get bored of something, you can really quickly change it up. And as you've seen in the examples, you can use gates to invert the bits. You can use LFOs. You can go really up into audio rate. You can just use a VCO to modulate the inversion. You could also use a sequencer, but keep in mind that LIPSK, the inputs of LIPSK really expect gate signals, so they will only react when the voltage exceeds a certain level. So now I'm sending in an audio rate pulse wave with a variable duty cycle. It's actually the EP output of orbit 3, which also follows the chaotic nature of orbit 3, but it just produces a pulse wave or a gate, which is really useful to use with LIPSK. You turn down the frequency. At this point, I can just as well remove the signal that's going into the filter. And just use the filter with the resonance turned up so it self-oscillates. So now we're really doing FM to a sine wave that's produced by the filter. try using one of the chaos outputs on orbit 3 as well to modulate another bit inversion. So again, I'm just using the output of this whole binary shebang here to modulate the frequency of a self-oscillating filter. And I'll patch in those dummy cables again, because we should be able to hear how it's actually a stepped voltage that's coming out of DREZNO when we only use a limited amount of bits. Let me even reduce the bit depth to only 2 bits. Let's remove this for a moment and reset this one. And you can not only see how with 2 bits, which results in 4 different voltages at the output, gives us a stepped signal, you can hear it as well. So let's remove these top ones. So we're just back to 4 bits. Now this is actually clipping my reverb. Let's turn that down. Let's get that gate coming from orbit 3 back in there. And this sounds really similar to Indian Resonator by Error Instruments, which also revolves around resonating waves. And let me show you once more that removing bits and inverting bits is something completely different. And I think it's important to show this because at first I thought LIPSK was just an expander that gave us a really easy way to change up the order of the bits, remove them, add other ones, etc. But LIPSK does really its own unique thing, which you can't do by just using DREZNO unless you use an external logic or inversion module. It's so much easier with LIPSK. And you can see that removing a bit and inverting a bit is something completely different. You can also see that anything you patch in here overrides whatever else is going on, because now manually inverting with 7 does not change anything. You need to remove the signal from the DAC output first. In this setup, I will show you how you can use DREZNO and LIPSK to manipulate the pitch sequence. For the moment, I have a sequence coming from Moscow 2. It's going through the scope. You can see it as the top trace, and from there it's going straight into my VCO. So for the moment, DREZNO and LIPSK are not in the signal chain. The things in the background are just a simple stereo delay coming from the Pico DSP. the other sound is just a wash from beats. So now I've rerouted the signal. Now it's going through the scope. First, you can see it as the top trace. From there, with the pink cable here, it's going into DREZNO, and then it's going back out of DREZNO into the scope. It's the bottom trace, and from there it goes into the vol per octave input of my VCO here. Now, as you might have noticed, immediately the pitch is quite a little bit off. Now, this can be adjusted with the sliders, but it's really hard to get it just as it was. So you can use the sliders for the input stage to attenuate the signal going in. But as you can see, there's only 4 bits active because the signal is so low. So I tend to set these sliders just by watching the LEDs, and I make sure that every bit is actually being used. I'm sure it's not necessary, but I like to do it this way. The offset here, as you can see, offsets the signal. So let's just keep it there. We can also adjust these at the output. And even though, as you can hopefully see on the scope, the signals are almost exactly the same, you can just hear that it's a little bit off. Let me find a setting here that works. So after some tweaking, I think this sounds okay. I've changed the pitch of the beads wash so it fits the new sequence a little bit better. So let's just start off by inverting bits. So as you might remember from all those confusing diagrams, bit 7 tells us whether a wave is above 0 or below 0. So for a CV signal that's above 0 to start off with, inverting bit 7 just pushes it below 0. Let me briefly change the settings on the scope here, because I want to show you what happens when you invert every bit. And as you might have guessed, inverting every bit just results in whatever signal that's going in being inverted at the output, as you can see. Now you can push this above 0 with the offset slider. And now I'm going to use an external clock to clock the conversion. I'm just using the VCA here as a multiple, because these LED cables aren't long enough to reach Pamela's new workout. It doesn't matter what the numbers are, you can see what the clock rate is here. And even though this clock is in sync with the tempo of the sequence that I'm sending into DREZNO, you can hear how there's little variations happening. You can also patch this clock into the output stage of DREZNO. And you can hear by playing around with your own clock, things get a little less precise. And even though I'm sending in a stable sequence which isn't changing, there's no probability, there's no random going on here. The signal that's coming out of DREZNO has a little bit of random in there, and this is due to quantization distortion, a concept that's really clearly explained in the talk the people of Xaoc Devices did at Schneidersladen. Now in this quick example I will show you how you can use LIPSK as an inverter for external signals. In this patch there's a random gate coming from Pamela's new workout. It's going through the VCA just so I can hook up this LED cable, because this cable is not long enough to reach the other side of my case. So this is the same gate that I'm sending to delta V, which I'm using in slew mode. And I'm sending an oscillator into delta V because I'm also using it as a VCA. So essentially there's a gate coming from Pamela, which is going into the delta V, which gives me an ASR envelope that attenuates my VCO. Now what I want to do is add a second VCO that only comes in whenever the gate of the first one is low. So I want them to alternate. Now normally inverting a gate that's, let's say, between 0 and 5 volts results in a signal that's alternating between 0 and -5 volts, which we still need to offset if we want to use it in a 2-quadrant multiplier or regular VCA. But you can also use DREZNO and LIPSK for this. Now of course DREZNO is completely overpowered to be just doing things like this, but I just want to show you that it's possible. Now to invert this signal I'll be using the gate pattern to patch into the inversion input on LIPSK. And as you can now see on the scope, which is connected to the DAC output, there's a signal that goes down every time the gate of the first VCO is high, but of course it's completely below 0 because it gets inverted, so we just need to offset this signal with the according slider on DREZNO, and this results in a gate being the opposite pattern as the one we're sending in. And if we use this gate to attenuate the signal of the second VCO, we can get them to alternate. going to end the video here. I think by showing you the things I did, you can get an idea what you can do with LIPSK in combination with DREZNO. Of course, there's also the fact that you can chain these modules in different ways, and you can just as well chain LIPSK behind YINA, but I'll show those things after I've done the video about YINA. I'll upload some of the diagrams that I've used on my Ko-fi support page. The link should be on screen right now. Ko-fi is kind of a support service just like Patreon is, but for me it works better because on Patreon you only have the option for monthly donations, and I really don't like that monthly aspect of that service. So I'm using Ko-fi instead, and although it's a support page, I post content that everyone can watch there as well. Sometimes I post videos that are already done but don't fit into my YouTube schedule yet, so some things you can watch there earlier than on YouTube, and that's for everyone, not just for supporters. Of course, there's some exclusive content for supporters in the form of patch breakdowns. I try to do a drone video twice a month. I call them Drone Monday, and every time I also record an extensive breakdown of the complete patch with all the sources, all the modulations, all the effects I'm using, but those are for supporters only. There's also a shop section on that page where I post user guides and little sample banks I made. Some of them are free or pay what you want, for others I ask a little amount of money, and the little money I make from the support page is all used to maintain the channel and to get interesting content out there. Everything there is related to the channel. If you're curious, go have a look. I hope you learned something in this video about LIPSK and a little bit about DREZNO as well. If there's any questions, please leave them in the comments. If there's some feedback, good or bad, please leave it in the comments as well. Reading the comments is always the best part of posting YouTube content, and for me that's what makes it all worth it. So next up is YINA. I know a lot of people are curious about that video, me being one of them, because I still need to make it. That will be probably for next month. So until then, stay safe. Thanks for watching. Bye.